Okay, 8.3 is an introduction to probability. Before we get into actually calculating, is mostly about the basics before we get into some more complicated situations. So let's cover some of the basics. So two events are considered disjoint if they cannot occur at the same time. Decide if the following events are disjoint or not. Being a doctor and being younger than 10 years old. You may argue that there may be extraordinary situations where that's true, but I would say these are two disjoint events. I would say very hard to get through med school by the time you are 10. It's probably not going to be a doctor. Being good at mental math and winning the lottery, these are not disjoint. I think people who win the lottery can be good at mental math. Luck and mathematical aptitude are not really related, and it's not one or the other, or possibly neither. So a sample space is all of the possible outcomes of the event, and it's a listing. So let's say you do two things. You roll a 6-sided dice and you flip a coin. What are the possible outcomes for this event? Well, you could roll a 1 and flip a heads, a 2 and a heads, 3 and a heads, 4 and a heads, 5 and heads, and 6 and heads. Or you could roll all of those same things but get a tails. So this would really be like the sample space. It's the set of the outcomes that could happen when you take certain actions. So generally speaking, basic probability, the basic chance of something occurring, is found by taking the number of successes divided by the number of possible outcomes. For example, if I was looking at the problem that we just had, if I wanted to find the chances of getting a tails, I look at the total number of outcomes that have tails in it divided by the total number of outcomes total, which would have been 6 over 12. And of course, that should be a 0.5 or a 50% chance of getting a tails, which makes sense when you're flipping a coin. The probability of the event is the number of outcomes in the sample space divided by the total number of outcomes in the sample space, including everything, not just the ones that have the thing you're looking for. So let's say you are shopping for graduation caps. In the story, caps come in 4 different sizes: small, medium, large, and extra large, and 3 different colors: black, white, and orange. Write out the sample space for graduation caps. Okay, we've got small and black, small and white, and then we've got small and orange. Same things with medium and large. We'll do X for extra large. What is the probability of buying a large orange cap? Well, how many things are large orange caps in our original? Just the one large orange out of 12 total. And you can turn this probability into a decimal or leave it as a fraction. It really is going to depend on which the problem. I don't care which one you do on the test. There's a 1 out of 12 chance. If you have to turn it into a fraction, I believe this is 0.083 repeating. What is the probability of buying a white cap? Well, how many of them are white? 1, 2, 3, 4. So 4 out of 12. It's about 0.333. What is the probability of buying a small cap? There are 3 smalls up here out of 12, which is 1/4. You can also have reduced this to 1/3. It's approximately 0.25. Well, it's actually equal to 0.25. We don't need the approximately in this case. And what is the probability of buying a pink cap? 0 out of 12. There are no pink caps, so 0. We call that something that is impossible. If an event is certain to occur, it has a probability of 1. The question, like, what is the probability you buy a hat? How many of those are hats? Well, all 12 of them. 12 divided by 12 would be 1. So if there's a guarantee to occur, it will have a probability of 1. If it can never occur, like the pink hat, it has a probability of 0. Every other situation should be between these two numbers, with larger numbers being more likely and smaller numbers being less likely. In a probability model, where all outcomes are disjoint, the total sum of all probabilities of the outcome must be 1. So that's like, if you're rolling a dice, your probability of rolling every number all added together should be 1, because exactly one event will occur and no more than or less than one event will occur each time you do something. So generally speaking, though, everything should have a number between 0 and 1, and the total of all of them should add up to 1 if it's a probability model. So let's see, you may get asked if something's a probability model or not. So let's look. You're taking a bag of M&Ms and recording the color each time you pull out one M&M. State whether or not the following is a probability model that could represent your experiment and why. So there's two things we have to check. Are all the numbers between 0 and 1? And number 2, do they add to exactly 1? So looking at A, looks like all of the numbers are between 0 and 1. So let's add 12 and 15 is 27, 39, 62, 85, 100. So 1.00. So this is, could it be a probability model? Yes, because it satisfies 1 and 2. So all the numbers were between 0 and 1, and it added to exactly 1. What about B? Could it be a solution? Just looking at it right off the bat, what do we notice here? Brown has a negative 0.12 chance of occurring. That means over the long haul, if you drew out a bunch of M&Ms, out of every 100 M&Ms, you would draw negative 12 brown M&Ms, which doesn't make any sense unless you're putting brown M&Ms back in the bag while you're doing this. No, it breaks rule 1 because brown has a negative probability. And then C, so C, it passes rule 1. I see only positive numbers, but what happens when I add these all together? 22 plus 25 is 47. 47 plus 13 is 60. 60 plus 20 is 80. 80 plus 23 is 103. Plus 11 is 114. So they add to a probability of 1.14. What that means is about every 7th draw or so, you're pulling out 8 M&Ms out of every 7 draws. So could this be a possible probability model for your experiment? No, it breaks rule 2. As the sum is not 1 of all probabilities. And that's really all the basics in 8.3. We'll get into more complicated situations moving forward in 8.4 and 8.5.